Now, I would like to introduce to you one method for us to predict the flow rate inside a pipe. Okay, because normally in our what you learn in fluid mechanics 1 and fluid mechanics 2, we usually use the Bernoulli equation to know the flow rate of pipes. Okay, it is true, and that method can be used, but the limitation is when we use Bernoulli equation, we must very sure about the inlet of the pipe, the inlet of the flow. For example, we have a tank here and the outlet of the tank. Okay, but in reality, in a real application, some of the application, we have the pipe network. So mean that to make sure that your house will be supplied of water. For example, we have so many housing area here. So we will link the pipe. Okay, I theoretically like this one. So means that if we have construction here, for example, we have a problem at this line, so the water still can flow from here to here and so on and so forth. So means that to make sure that all user can get water supply, so we need to have a pipe network. Okay, when you have a lot of pipe network, means if you want to calculate the flow rate by using the Bernoulli equation, you need to construct a lot of Bernoulli equations. So means, for example, if we have a network like this one, so means you need to compare the Bernoulli equation from this point to this point, for example, and then from this point to this point, from this point to this point, and so many more. So because it will generate so many Bernoulli equation, so means that it is hard for us to solve the problem. Okay, because of that, okay, one researcher named Hardy, he managed to simplify the equation, simplify the losses equation, and then they will comes with the trial and error method, as known as Hardy-Cross method. So as note, the Hardy-Cross method is an interactive method for determining the flow in pipe network system where the input and outputs are known, but the flow inside the network is unknown. The method was first published in November 1936 by its namesake Hardy-Cross, a structural engineering professor at the University of Illinois at Urbana-Champaign. The Hardy-Cross method is an adaptation of the moment distribution method, which was also developed by Hardy-Cross as a way to determine the moment in interminated structure. The introduction of the Hardy-Cross method for analyzing pipe flow networks revolutionized municipal water supply design. Before the method was introduced, solving complex pipe system for distribution was extremely difficult due to the non-linear relationship between head loss and flow. The method was later made obsolete by computer solving algorithm employing the Newton-Raphson method or other solving method that prevent the need to solve nonlinear system of equation by hand. The Hardy-Cross method provides a system for calculating the value of the correction to be made, each loop or junction being considered in turn and corrected, assuming that conditions in the remainder of the network remain unaltered. Two main assumptions used in Hardy-Cross method. One, the losses of head between any two junctions must be the same for all routes between these junctions. So for example, for condition number one here, so for example, we have a pipe network of A, B, C, and D. And then we need to imagine that the head loss in pipe BA plus head loss in pipe DC must be equal to the head loss pipe AC plus head loss pipe in BC. So this is actually showing you the idea of the losses in parallel pipe. Previously in our notes, we have a pipe like this one. Okay, because it flow because the water flows in parallel direction. So we assume that the losses at this section is equal to this section and equal to this section. By right, it carries the same meaning of this one. So, and then number 2 assumption is the inflow to each junction must equal the outflow from that junction. So it means that at one junction here, the total inlet must be equal to the total outlet. So Q for B plus Q for C must be equal to the Q for A here plus the Q for D. So this is the idea of conservation of mass because we are dealing with water. So water is incompressible. So means that if the system is full, so means that if you put another 1 liter, so means that at the outlet there must be 1 liter need to be taken out. The method of balancing head use an initial gas that satisfy continuity of flow at each junction and then balance the flow until continuity of potential is also achieved over each loop in the system. This method can be used if total flow rate is known. Head and pressure at junction is not compulsory items. So the idea is very simple. As mentioned here, actually we need to guess our initial condition, and then we need to do the correction. So means that if the flow is too small or too low, so we need to increase the section of that section, and then we need to reduce another flow rate because the inlet and the outlet must be the same. Okay, let's say because we assume that the total loss, that the losses for each section is the same, so we could write like this one. So we have HF is equal to FL over D V square over 2G, and then we simplify it into this term, and then we write as K times Q square. So means that the Q here is actually equal to this term. So and then because we have a situation like this one, so means that if we calculate the losses, if we calculate it counterclockwise, so mean we calculate from here, so we add heat from this direction to this direction to this direction and to this direction, it must be equal to our summation from if we add them in another direction. So means here to here to here and to here. So means that it doesn't matter what rotation you take, whether you want to add in counterclockwise rotation or in clockwise rotation, the total losses for this pipe must be equal because losses is actually not depends on the direction. So we use this idea to calculate here. So we believe that head loss in pipe, which in the clockwise direction can be written as this one, Kc times Qc square. So C here means the clockwise. So and then the head loss for the counterclockwise can be calculated as this one, Kcc times Qcc square. And then if our calculation is correct, so means that our head loss that we calculate in clockwise must be equal to the losses that we calculate in counterclockwise. As I said, if we have a network here, it doesn't matter if you want to add all the losses starting from here to here to here to here and to here, because it will give you same result if you calculate the losses from here to here to here, here and here. So ideanya ialah untuk kita mengira losses, tidak kisah kita mengira berdasarkan pusingan yang mana. Sama ada awak nak mengira ke kanan, ke kiri, atau awak ingin mengira ke kanan, kedua-duanya akan menghasilkan jawapan yang sama. Okay, itu sebab kita kata di dalam step ini, kita samakan calculation losses kita ketika kita mengira ke kanan dan ketika kita mengira ke kiri. Okay, so means that if we equalize this one, okay, so means that our answer will be balanced. So the left side and the right side will be balanced. Okay, however, for sure, because as I said, we need to guess. For sure, in our assumption, in our first assumption, we cannot balance between the clockwise and the counterclockwise. So means that, for example, our assumption is not correct. So means that to correct our assumption, we need to take, for example, here the clockwise here is bigger compared to what we have in counterclockwise. So if the clockwise is bigger, what we need to do is we need to take small amount in clockwise flow rate, and then we need to put it into the clockwise counterclockwise amount of flow rate. Okay, please make sure that you write as this one. Please make sure that you write the QC minus delta Q in bracket square, and then you add the same amount of this delta Q to this one. So mean you need to write QCC plus delta Q in bracket square like this. And then the amount of delta Q must be equal, because the same amount you take from the left is need to be transferred to the right. So mean the delta Q is actually the same things. So and then what we need to do is we need to expand this term so we could get this one, and then to simplify it, so we could say that delta Q square, because delta Q is very small, so if we square the amount, so the amount will become smaller. So and then we could neglect the delta Q square here. So and then we could rewrite the equation become like this. So we have the total amount, the sigma means the total amount of Kc QC square minus KCC QCC square, divide by 2 in bracket sigma Kc QC minus KCC QCC. So and then we need to rearrange, or we need to rename the equation here by using this term. So we know that the losses is equal to KQ square, and then we could write as KQ is equal to losses over Q. So and then we substitute this term into this equation. So we could get this term. So and then please bear in mind that the C here means the clockwise rotation, and CC here is counterclockwise rotation. So and then in Hardy-Cross method, okay, in first half of the calculation, we need to determine the value of delta Q. But the final answer is not the delta Q. As I mentioned here, calculation will be done many times until the value of delta Q is approaching 0. So the delta Q is actually the indicator whether your answer is correct or not. Okay, if you get delta Q is equal to 0, means your answer is 100% correct. But if you cannot get the delta Q is equal to 0, what you need to is you need to do by so many iterations. You need to do the first trial, second trial, third trial, until the delta Q will become smaller and smaller. Okay, bear in mind again here, The delta Q is not the final answer. You need to propose new flow rate as your final answer. So I will describe to you, I will explain later how to get the final answer based on the value of delta Q. Now, I hope you could understand the derivation of delta Q here, and then you need to know this calculation is based on the rotation, the clockwise and the counterclockwise value.